Now we're sharing. Now we're recording. Now we're sharing. Okay, now we're back to where we were. Okay, so we're going to start this then. So the whole idea is to make sure that we can identify what are derivatives and when we can take derivatives, and then what we can do with them in complex analysis. So we're going to start with something that's called the Cauchy-Riemann conditions. And what it boils down to is if you have a derivative for a complex function, it doesn't matter which direction you approach that derivative. So if we consider the complex plane in x and y, and we have a point z naught, right? It shouldn't matter if we approach it, say, with delta x equals 0, but delta y approaches 0. That is, we're getting close to that point as y is the separation from wherever we are in y approaches 0, or if delta y is equal to 0 and delta x approaches 0. That is essentially a necessary condition for a derivative to exist. And the way that we can write that then is, again, we're going to consider f, our complex function is u plus I v, where u and v are real functions of x and y, right? So for this to be true, we have the partial of x is equal to, the partial of u with respect to x is equal to the partial of v with respect to y, and the partial of u with respect to y is equal to the negative of v with respect to x. And these are the conditions, or this is the necessary condition for df of z dz to exist and be well defined. Okay. And I'm going to skip the proof of that. The proof is in your book. It's essentially looking at the limit as x goes to 0, delta x goes to 0, and y goes to 0. But what this does then is allow us to define what are called analytic functions. Okay, so analytic functions are basically functions in which f of z is differentiable. That is, it meets the criteria in B.1 and single valued in some small region around z naught. There are some special cases where you could have multiple values of the derivative or of f of z. We'll get to those if we need to. And what this means then is that you can define, you can define f of df dz in terms of the partials of x with respect to x and with respect to y, but if we use the Cauchy-Riemann conditions, we can write df dz as du dx plus I dv dx, or df, actually, partial with respect to x. And that's just because we have in B1 a way of connecting the derivatives of v with respect to y and u with respect to y to the derivative with respect to x. Okay. Okay, so that may not seem startling. I don't know. But it does have some interesting implications. So it's useful to look at a couple of examples. And again, your book has some of these, but as usual, a fair amount of steps are skipped. Let's start with one straightforward example, and ask, is f of z over, if f of z is equal to 1 over z, first, is this an analytic function? Okay, so is this analytic? So in order to do that, we check the Cauchy Riemann conditions. We write, oops, f of z is equal to 1 over x plus iy, which we can beat into form by multiplying top and bottom by x plus iy. So that gets us x plus iy over x squared minus y squared. So that means that this is equal to x over x squared plus y squared plus I times y over x squared plus y squared. In other words, this is u and this is v. Okay? So I'll leave it for you to verify, because this is pretty straightforward, that du dx is equal to minus x squared plus y squared over x squared minus y squared squared, and dv dy is equal to x squared plus y squared over x squared minus y squared squared. So in that case, it's not analytic for this function. This, one of the reasons why we start with this function as an example of non-analyticity is because of the role it plays with the Cauchy integral theorem, and eventually the residue theorem, how we're going to transform these intervals into algebra. Okay, so this is a first, basically a check. All right, straightforward? Okay, one other example. Can I move this? Let me know if I'm going too fast, because I know this is going to be kind of equation heavy today. Another example is the natural log of z. And your book does cover this, but does skip some steps. So we looked at 1 over z. That's not analytic. That means it doesn't have a derivative is defined the way that we would in the complex plane. But what about ln of z? Well, we can write this as ln of r, right, plus I theta plus 2n pi I. Right? That includes all of the multiple variables, and we can focus on the principal variable, but that means that this is equal to ln of r plus, say, theta I. We're just thinking about the principal value, okay? All right. du dx is straightforward. That's just 1 over r dr dx. And that's equal to x over r squared. Dv dx is equal to d theta dx. And that's a little trickier, right? That's equal to d dx of theta, but that's d dx of the inverse tangent of y over x. Right, so if you know that, or you look that up, that's equal to 1 over 1 plus y over x squared, and then times the value of the derivative of y over x, so minus y over x squared, which equals minus y, if you do all of this out, over x squared plus y squared, or minus y over r squared. And then we could do the same thing for du, dy. That's just 1 over r du dy, and that shouldn't be a surprise. That's equal to y over r squared. Why this is doing this. And then dv dy is equal to x over r squared from the same kind of argument that we have up there. So if you look at that, you can see that that satisfies the Cauchy-Riemann condition. So that means that you can define, so this does, so it's analytic, and so d ln z dz is just basically du dx plus I dv dx in this case. So interestingly enough, once you work that out, that gives you 1 over z, which is what you'd expect, right? So maybe not too surprising. And there are other cases that you can try at home. You can ask, is z squared analytic? And if so, what's its derivative? You can get more interesting cases I think you have in your homework, e squared to the minus y squared times cosine of 2xy plus I sine 2xy. Is that analytic? And if it's analytic, what's its derivative? Okay. So anyway, this whole first part, the whole first few minutes of today is just to define what a derivative, under what conditions we have a derivative. That means it's essentially path-independent approach toward a function, a position at a function. And then once we know that, because of the way we've defined it, all we have to do really is take the partial with respect to x. Okay, we could do the partial with respect to y if we wanted to as well. How are we doing? Good? All right. All right, on to contour intervals then. This is why we're doing this. How many people have seen contour intervals in complex? I mean, they're different from line intervals. Okay, that's cool. So contour intervals are a way of basically taking the interval around the contour of a region in order to not have to do the, or in order to have to not do the interval inside the region in complex space. In other words, I mean, it's a bit like, I guess one analogy that you might have run into is the delta function, where you can get the value of the function without having to do the actual integration. So we'll start with Cauchy's theorem. And the idea is that we'll let C be a simple closed curve. With continuously turning tangent except at maybe a finite number of points. I'll get to what this means in a minute. If our function in complex space of Z is analytic, on and inside C, then, and this is where it's really important, the contour integral, that is the integral around that contour of f of z dz is equal to 0. So the idea here is, right, you have some simple simple contour. By what we mean by simple closed curve means that you should be able to shrink it uniformly all the way to its center without overlapping, right? So that, in other words, the curve doesn't cross. Right? I mean, this is sort of a straightforward way of understanding simply connected. I'm sure there are better ways of doing it in topology, but this is the way that essentially I learned it. So if you can shrink it down without passing part of it, it's simply connected. Okay. The proof of this is not exactly that difficult, but I don't want to spend too much time on it. But it does involve using Green's theorem. In other words, if you consider the contour integral of f of z dz, that's the integral around this contour of u plus iv times dxi dy. That's just the definition of our integration, which we can break apart, right, as this into u dx minus v dy. You can see why maybe Cauchy-Riemann conditions are important now, plus an imaginary term, c, is y, times v dx plus u dy. And where we use Green's theorem is that we're looking at contour of, say, p dx plus q dy, and that's set equal to the area integral of dq dx minus dp dy dx dy. But when you do that, so when you go from here, which we set up, I don't know why it's doing this. We set this up here. You go from here to here. This is where we use the Cauchy-Riemann conditions to show that this is equal to 0. Okay, so as long as the function is analytic, and it's the same is true with the imaginary interval. Okay, so as long as it's analytic, this interval is 0 once you're going all the way around. So it's a closed interval. Okay. So far, right? What's important is when it fails, or when this isn't equal to 0. So let's look at another example. Let's consider the contour interval of the contour c of the function z to the n dz, where c is a circle centered at 0. So one way to do this is to go back to our definitions for z, right? So what do we have here? What can we write as z in polar coordinates? What did we do before?
RE to the I theta.
Right, so we can write this as RE to the I theta, which means that dz is equal to I R e to the I theta. Okay. So now we can look at this integral, and we'll split it up into two. Sorry about this. So two cases. For n not equal to -1, right? If we make all of this, these substitutions, we should have this transforms into 1 over 2 pi I times the integral around that contour of z to the n dz. And that's equal to r to the n plus 1 over 2 pi times the integral from 0 to 2 pi, since we're going over the circle, of the integral of I to the n plus 1 theta d theta. Okay. That's a straightforward integral. So this is equal to 2 pi I n plus 1 all to the -1 times r to the n plus 1 times e to the I n plus 1 theta evaluated. I'm having some problems with the network. That's why it keeps doing that. I'm sorry. Evaluated from 0 to 2 pi. All right, so what's the result of that integral? So ignore the front part out of here. What happens when we evaluate e to the I n plus 1 theta from 2 pi to 0, or from 0 to 2 pi?
1 minus 1.
Well, if you expand what this is equal to, this ends up being equal to 0. There's another way of saying also that z to the n is analytic. Now, if we look at the case for n equals -1, we have 1 over 2 pi I times the integral around this contour of dz over z. That's equal to 1 over 2 pi I, an integral from 0 to 2 pi of r e to the I theta over r e to the I theta d theta. And that's equal to 1 over 2 pi times the integral from 0 to 2 pi d theta, or 1. So there's something really deep here that's leading us eventually somewhere. If the function is analytic, this contour integral is equal to 0. If it's not, then we have a way of finding the result of that integral by looking how that's evaluated at a particular point where it fails that analyticity. And that's ultimately what's going to lead us to Cauchy integrals. Okay, so I'm trying to break this down. I'll pause here if anybody has any questions.
In Cauchy's theorem, did you define, or is it important, what continuously turning tangent accepted a finite number of points means?
So that's another way of saying that if you were to collapse that down, not only if you were to collapse that down, you all arrive at the same point, but you're going in the same direction. So typically we define it as going counterclockwise. It'll change the sign if you go the other way, but as long as you're not going back and forward. Yep, thank you.
I have a question too.
Sure.
The 1/2 pi I in front of the integrals,
Mm-hmm.
is that the circumference of the circle?
Right. So that comes from yes, from because it's 2 pi. Yeah. Mm-hmm.
Okay, and does that mean that why isn't there an well, I guess the radius. Where did the radius go?
So the radius for that dropped out because we're only integrating around theta.
Okay.
Right, so the integral is just d theta.
Okay.
So, and this is a particular or a general case for R. We're going to look at when we expand this to different values of absolute values of z. But the idea is that this contour integral is that, and I think if you look, where is it? On page, well, 478, 479. It goes through the fact that we're integrating along this contour that we've defined. And the plan here is that we're going to use this result in particular to make our contours either include or exclude singular points, where a derivative or a function would become non-analytic. And those are called poles or singularities. And then once we identify those, we can actually pop out the integral and get the principal form, principal value of an integral. Which sounds like gobbledygook, I know, at this point, but we're headed somewhere. In fact, right now. Any other questions?
I have a question.
Sure.
Why did you choose -1 again, and like not -1, or like why that?
Okay, that's a good question. There are two different cases, right? And it's based on this right over here. Right, so that separates this out into either a case where whether the integral is analytic or non-analytic. Okay, so for n not equal to -1, if you think about the original problem up here, we knew from sort of the first example that f of 1/z is not analytic. So this is a demonstration for n not equal to 1, in essence, that z to the n is analytic on this region. So we just separated out that special case. Okay. All right, any other questions? This is good. Okay. All right, so where this leads us then is Cauchy's integral formula. We'll start with a statement. So if f of z is analytic on and inside a simply closed curve, then the value of a function at a is equal to 1 over 2 pi I times the integral of f of z over z minus a dz, with a inside the contour. And again, what we're looking at is some contour that is simply connected, simply closed, right? And the idea here is that we're going to try and find integrals that look like this. This is f of z, sorry. And it may be that f of z is equal to 1, right? But we're going to be trying to identify cases where we have these, essentially this form of 1 over z minus a. The proof of this is a little, well, it's your typical physicsy proof. I'm not going to go over all of it because I'd rather get to examples and physics cases, but the idea is if you have a point A, you can construct a contour C that surrounds the point A, essentially the singularity, and then shrink that that small space that has a radius r, make that r go to 0. The reason why this is interesting again is this thing right here, and now I put an arrow here. It makes it look like a 2. And realize what this is saying. This is saying that the value of the function at a, at that point, is equal to that integral. We're going to turn this around so that we don't have to do the integral in order to evaluate that integral. So, for example, let's see, there's several examples we can look at. Let's consider the case of an integral. Here we'll just make up some integrals. The contour of sine z dz over 2z minus pi. Now, the result of this integral depends on what we make our contour. Right? So if we make our contour such that z is equal to 1, or we make the contour so that z, the absolute value, is equal to 2, you'll have 2 different values for the integral. Right? In other words, if we look at what this integral is equal to, we can factor out a 1/2, and then we have sine of z dz over z minus pi halves, right? So that's about 1.5-ish or so. So if we use this contour, right, the singularity is not inside the contour. If we use this contour, it is. Okay. So what do we do with this? If we choose our contour carefully, then this integral is equal to 1/2 times the contour, or times the integral of sine z dz by z minus pi halves. That's equal to 2 pi I times the function evaluated at the point A. The point A is basically where this function blows up. So that's equal to 2 pi I times sine of pi halves, right? And that's because we've identified alpha of z is equal to sine of z. Right? If we go back, just real quick here so we can show this, right? Our job when we do complex analysis like this is to identify what is our alpha of z that we're interested in, and then where does it become non-analytic, okay? And once we've identified that, we can evaluate this interval. Now this is equal to I, or to 1, right? So this interval has a value, since there's a 1/2 there, of I times pi. Okay, as long as we include that singularity. We don't have to use a circle. There's another example, actually a couple of examples in your book where you can use a square contour. So for example, we can look at the contour integral of e to the 3z dz over z minus ln 2. And if we want to look at this or solve this, first we need to know where this blows up. So our singular point A is equal to log of 2, which is basically 0.693. That's less than 1. So we could do this with a circle, unit circle, or we could bound it to our contour. So since z is equal to 0.69, will be located right here. Z is equal to A, and it's a real number, right? So it's on the real number axis. And then we could bound this by a contour, let's say a square contour, that goes out to 1i and down to minus 1i. Right. In which case we could just do the contour integral in those 4 steps. I think your book does something it's pretty similar in one of the examples. If you do that with this contour, you end up with, again, 2 pi I times e to the 3 ln of 2, because this, again, is our f of z, and that equals 16 pi I if we do all the work. All right, so those are 2 kind of, I mean, really abstract. This is just doing intervals. I'll do one more example before we look at derivatives so we can develop the Laurent series. This one is a little bit more, has a little bit more application to physics. Hooray. So this is related to the Dirichlet problem for a disk. So the Dirichlet problem for a disk, and there are a number of ways that you can consider this. As you consider, this could be this is a description of the steady state temperature, say temperature, usually U is a function of R and theta, where the temperature is specified at the edge of the disk. Okay, it's a Laplace equation solution. And there are, of course, different ways that you can solve this. We have, say, a radius r, and we want to know what is the temperature at radius little r, where little r is between 0 and capital R. Okay, so how would we go about doing this? Well, you can show that the temperature is equal to 1 over 2 pi, the integral from 0 to 2 pi, of what's called the Poisson kernel, which is r squared minus r squared over r squared minus 2r cosine theta plus little r squared times your boundary value, d theta. Right? Now, that obviously can be a pretty complicated function to integrate. The way that we would approach this in complex analysis is to reconstruct the Poisson kernel. So I'm going to focus just on the Poisson kernel for now. So just to make things simple, let's let g of theta just be equal to 1, some constant. We'll just ignore the units. And then rewrite the Poisson kernel as the real part of r plus little r e to the I theta over r minus little r e to the I theta. And you could do that because if you expand this out, this becomes r plus little r e to the I theta, r minus r e to the minus I theta over r minus r e to the I theta times r minus r e to the minus I theta. And that's equal to r squared minus r squared plus 2ir r sine theta all over r squared minus 2rr cosine theta plus r squared. So if you take the real part, you get what that kernel represents. This derivation is just out there. The reason why we want to do this, though, is to bend our integral to our will and write it in terms of an f of z over a singularity. Okay. So if this Poisson kernel can be written in this form, then again, we can go back to how we've defined z. So let z be equal to little r e to the I theta with r fixed. In other words, we're finding what the temperature is in this particular problem at a specific r. And in this case, I mean, the result's not going to be particularly surprising because I've made the boundary condition, right? The Dirichlet problem is essentially what's the solution to Laplace's equation given the boundary conditions, periodic boundary conditions. So we have that. Then we can look at dz d theta, which is ri e to the I theta, but that's just equal to iz, which means that we can go back to that integral, and that's 1 over 2 pi from 0 to 2 pi of that original form of the Poisson kernel, d theta. And that's equal to the real part of 1 over 2 pi I times the integral now for z equal to the absolute value of z equal to r, right? So remember in our way of expressing in polar coordinates complex numbers, that gives us the length. And now we're left with r plus c over r minus c dz over z. Now we can use the Cauchy integral theorem. So 1 over 2 pi I in the region where z, absolute value of z is equal to r on this disk. So we're actually doing that contour around the edge of the disk of r plus z over z times r minus c dz is actually equal to 2 integrals. And this is another reason why I want to do this, this example. One of the key things that you're going to see probably on Friday is that you need to break up the arguments for these integrals into fractions. So we can rewrite this expression as the integral over z is 1 over z plus z over r minus c dz. Okay. In other words, if you combine these two, you should get what we get over here. All right. That means that we have 2 integrals to consider. We have 1 over 2 pi I with z equal r of dz over z. Happy day, we know what that is. Minus 1 over 2 pi I z equal to r 2 dz of z minus r. Okay. So what's the value of that integral?
The integral is 1, so it's 1 over 2 pi I.
Yep, so this is equal to 1. What about this integral? There's a hint here given how we set up the problem, right? R is less than R.
Zero.
So this is equal to 0, right? If the singularity in this expression, right? So our f of z is 2, so no big deal there. But our singularity is outside our region, our contour, then this is equal to 0. So essentially, right, what we've shown is if you have a uniform temperature disk, then the temperature's uniform. Right, so that's a long way to go to get to a simple answer, but you can imagine if we go all the way back up here and we use a different function on the contour, that this might be a greater simplification for a more difficult problem. That's a way of motivating what we're doing here. Okay. Are there any questions on that? Okay. All right. We do have a few minutes, and I do want to get to one last thing before we head off today, and that's derivatives. So we've defined when a derivative exists, even though it may not look like it necessarily, we've used them in the integrals. Now we want to say something about what these derivatives have to do with these integrals, other than being anti-integration. So we can consider the value of the nth derivative evaluated at z naught, wherever that point of interest is equal to n factorial over 2 pi I times the contour integration of f of z dz over z minus z naught to the n plus 1 dz we're going to state this, and ultimately this is headed toward essentially a complex function version of Taylor expansion. This means is something like f prime of z naught is equal to 1 over 2 pi I times the contour integral of f of z over z minus z naught squared dz. F double prime of z naught is equal to 2 over 2 pi I times f of z over z minus z naught cubed dz, and so on. Why do we care about this? One, this hopefully you're seeing that this is setting up complex power series, and in particular complex Taylor expansion. And then ultimately we can use these expansions to evaluate these contour intervals more easily than what we did this morning. Okay, so time running out, probably going to stop it here. I realize that this is probably very new for a lot of you, so I would encourage you to look back at this and go over the reading. It is confusing, but the main idea here is and what we've tried to accomplish this morning is identify the conditions under which derivatives exist, and then what are the properties of those derivatives. And because we're dealing with a complex plane, we have to do this contour integral. And then the surprising thing about this contour integration, which is something that we discovered with trying to look at the derivative of 1 over z, is that we can find the value of an integral if we choose our contour region carefully. And if we do that, then, and the thing that's hinted at our treatment over here is that if we're clever, we can take in a complex integral, break it up into these partial fractions, and then each one of these partial fractions will give us a result in a power series, which gets us all the way back to the beginning of this lecture. The whole point of this is that there are physical systems in which complex analysis is important. And if you can choose the contours carefully, then you don't have to do the integration. You can essentially do the algebra instead. Okay. Big breath. This is not obvious stuff. But I think that on Friday, when we get into complex series and the Laurent series, some of this stuff will pull together. If you have any questions, of course, stop by my virtual office hours or send me an email. But also just be kind to yourself. This is something that in my experience in teaching this course and in having taken a course like this is kind of the weirdest part in the early part of the class. So if it seems non-obvious, it's because it is. Okay. All right. Any final thoughts or questions? Okay. I'll see you guys whenever. Have a good day.
Thanks. Bye.
Thank you.
Bye, Willa. Bye, Meg.
Bye, Allie.
Bye. Here we go.